Nuclear reactions. Before we look at nuclear reaction, let's look at nucleus of an atom. This is, you might already know this. This is just kind of like a review of some material from before. An atom consists of nucleus in the middle. This is the densest part of an atom, the tiniest and the densest part of the atom. It consists of two components. One is protons and neutrons, contains protons and neutrons. Protons have a positive charge, they have a charge of +1. Neutrons have a charge of 0, meaning they are neutral. Around the nucleus we have electrons, which have a charge of -1. You might also be familiar with their masses. So when we go to mass of each of these components, electron has a negligible mass, meaning 0, because it's negligible in mass when compared to protons and neutrons. Protons have a mass of 1 AMU, 1 atomic mass unit. AMU stands for atomic mass unit. Neutrons also have a mass of 1 AMU. These sometimes are written as symbols, and this is what you see right here are the symbols of each. What's written on the bottom is usually the charge, and what's written as the superscript is the mass. So electron is -1 0, which means -1 is the charge and mass is 0. Proton is 1 1, 1 positive charge, and mass is also 1. Neutrons are neutral, so the charge is 0 and mass is 1. There are some more terms that you will see in nuclear reactions. That's why I want to review those again, but you might know, or well, you should be familiar with these from before as well, but we'll quickly review them. Those terms are mass number, atomic number, and isotopes. Okay, so what is mass number? Mass number of an atom is defined as number of protons plus number of neutrons, and mass number is usually abbreviated with the symbol A. So A stands for protons plus neutrons that are present in the nucleus. Atomic number is called as the number of protons of any atom. This number is usually represented by the symbol Z, so atomic number is also written as Z. This number right here is the identity of the element. So if you look at periodic table, you will find the atomic number always written there. For example, carbon, on the periodic table, if you pull up your periodic table, you will always see the number 6 written there over carbon. That number is the atomic number of carbon, which means it is the identity of the carbon. For example, every player, athlete usually has a jersey and a jersey number. That's what this is. Okay, it's its identity. If this number changes, that means it's no longer carbon. If an atom has a number 8 as its atomic number, that means it has to be oxygen. Why? Because there's only oxygen in this universe that can carry the atomic number of 8. Carbon is the only atom that can have an atomic number of 6. And what is this number? This is number of protons. So carbon always has 6 protons, oxygen would have 8 protons, nitrogen would have 7 protons. And where do you get this number from? From periodic table. As long as you know the identity of the element, you can find its atomic number. For example, chlorine. I'm telling you this atom is Cl. So if I ask you how many protons it has, you look up the periodic table, find its atomic number. The atomic number of chlorine is 17. So this number at the bottom is 17. It's always written as the subscript, and mass number is always written as the superscript. And usually this is the symbol of the element. Okay, so for example, carbon. If I tell you I'm looking at carbon 12, then this number that I give you is actually the mass number of the element. Mass number again means protons plus neutron, and this number, mass number, is not provided to you on the periodic table. Okay, this is not same as the mass of the atom. It is the mass number of the atom. There's a difference between the two terms. Mass of the atom is weight of the atom. That is not given to you. That is on the periodic table. Okay, and mass number is the number of protons plus neutrons. This will be provided to you. You cannot find this number anywhere on the periodic table. Okay, so if I say carbon 12, that means I'm telling you it has mass number is 12 and atomic number is 6. Where do you find the 6 from? Periodic table, because I told you it's carbon. Okay, now the next term is isotopes. What are isotopes? Most of the elements that exist in this universe or exist in nature, they have isotopes. What are isotopes? Isotopes are atoms with the same number of protons but different number of neutrons. So you can also say they have same atomic number but a different mass number. Okay, so their Z will always be same, but their A will always be different. Those are isotopes. Example, carbon has 3 isotopes: carbon 12, carbon 13, carbon 14. If I give you this number, that means I'm giving you the mass number of the element. So if I give you these and I ask you how many protons, neutrons, electrons do all of these have, you can figure that out very easily. Okay, for example, let's make some space here first. Carbon 12. How many protons, neutrons, and electrons? Okay, every atom is neutral. Okay, every atom, if I say carbon, it's a neutral atom. Neutral means it has the same number of protons and electrons. Protons carry a positive charge, neutrons carry a negative charge. For the atom to be neutral, the number of positives should be equal to number of negatives. So that's why protons is equal to electrons. Sometimes if any element carries a charge, we call it ion. Okay, for example, if I say O2 minus, that means this is oxygen with a charge of 2 minus. The charge is always written as a superscript on the right side. When would an atom have a charge? When either it has lost an electron or it has gained electrons. When it gains electrons, it gets a negative charge. When it loses electrons, it gets a positive charge. Every electron lost is one positive charge. Every electron gained is a negative charge. Okay. All right, coming back, how many protons, neutrons, electrons in each of these? Carbon 6, 12 would have 6 protons. How many neutrons? 12 minus 6, which is 6. How many electrons? Because there is no charge on the top right, it is also 6. Carbon 13. How many protons? 6. How many neutrons? 13 minus 6, which is 7. How many electrons? Also 6 because it's neutral. Carbon 14. Protons is 6. Neutrons 14 minus 6, which is 8. How many electrons? Also 6 because no charge. So majorly, what is the difference in all of these? They have same protons but different number of neutrons, and that is why we call them isotopes. Okay. Another term that you will commonly see being used is nuclide. Nuclide simply refers to the nucleus of an atom. Okay, and remember, what does a nucleus contain? It is protons plus neutrons. So when we say nuclide, we basically are talking about nuclear composition of an atom. You can try the question on your own. Okay, for example, it says compute the nuclide notation and calculate the number of protons, neutrons, and electrons for each of the isotopes of chlorine. Chlorine 35, chlorine 37. Again, if this number is given, that's the mass number. Chlorine 35 would be what? Cl, mass number is written on top, so Cl 35, Cl 37. Now, how do I find the atomic number? Periodic table. 17, 17. So these are the notations. Question is how many protons, neutrons, electrons? Protons, 17 here, 17 here. Neutrons, 35 minus 17. Oops, 35 minus, why can't I write minus? Oh, 35. Okay, maybe I'm just gonna, okay, I'll just write it here. When it comes to neutrons, this is chlorine 35, chlorine 37. Neutrons will be 35 minus 17, 37 minus 17. Electrons, in this case, all 17 and 17 because it has no charge. For example, if I said Cl negative, then we know that the protons is 17, which means electrons would be, because it has a -1 charge, which means it has one extra electron. So ideally 17, but because it has a negative charge, 18 electrons. If I say, let's say Cl2 minus, even though it doesn't exist, Cl, atomic number 17, so proton 17, which means electrons is 2 extra. That's why 2 negative charge, so plus 2, 19. If I say Cl2 positive, that means protons 17, electrons positive charge, so it has less electrons, so it lost 2 electrons, which would give you 15. Okay, so that's how you find the nuclear composition, or the composition of the whole atom. Okay, now what are nuclear reactions? So far, most of the people are familiar with chemical reactions. For example, CH4, methane, plus oxygen gives carbon dioxide and water. This is an example of a chemical reaction. What happens in a chemical reaction? Usually, atoms are involved and bonds are either broken or formed. For example, here carbon is bonded to 4 hydrogen atoms. Oxygen here is bonded to itself. In the product, carbon is bonded to oxygen now, and hydrogen is also bonded to oxygen. That gives you water. So what's happening? These bonds are breaking, and carbon is making a bond with oxygen, and it's forming CO2 and water. Okay, so bonds are broken, bonds are formed, but the identity of the atom does not change. For example, in the reactant side, I have 1 carbon, product, I have 1 carbon. I have 4 hydrogens here, I have 2 times 2, 4 hydrogen here. So the number of atoms are same, they do not change their identity. But in case of a nuclear reaction, the nucleus participates. In case of a chemical reaction, only electrons participate. Nucleus is never involved. Protons and neutrons are never involved. But in nuclear reaction, protons and neutrons are involved. For example, here, uranium is changing to Ba, barium, and krypton. The atom has changed its identity. That is called nuclear reaction or nuclear transmutation. Nuclear changes in most cases alters the number of protons in the nucleus of atom, causing a change from one element to another, and that is called a nuclear reaction. So chemical reactions, only electrons. Nuclear reaction, protons and neutrons, meaning the nucleus. So their nuclear reaction and chemical reactions are different from each other. And how? Nuclear reactions, atoms never change their identity. Never. Okay, atomic number never changes. Nuclear reactions, though, most of the times atom of one element will be converted into atom of another element, and atomic number will almost always change. Chemical reactions only involve electrons, means making a bond or breaking a bond. Nuclear reactions involves protons and neutrons. Chemical reactions, the total quantity, meaning the mass or the matter, never changes. Law of conservation of mass. Mass of products is same as mass of reactants. There is a small change in energy. For example, you might remember exothermic reaction or endothermic reaction, right? So there is a small energy involved. But in case of nuclear reactions, mass changes a lot. Same thing, energy changes are relatively very large. You might have heard that in nuclear reactions there's a lot of energy involved, right? So it can solve our energy problems. Why? Because very large energy changes. Rate of a chemical reaction, we can speed it up, we can speed it down, we can control the speed. How? You can change the temperature, you can change the concentration of elements, catalyst, right? So all these things can change rate of a chemical reaction, but you cannot change the rate of nuclear reaction. It does not depend on temperature or catalyst, but it does depend on the number of nuclei, not the concentration, but the number of atoms. Okay, so nuclei means nucleus, and who has nucleus? Atoms have nucleus. So if you want more nucleus, you need more atoms. So if you have more atoms, the nuclear reaction will be faster. If you have less atoms, nuclear reaction will be slower. Okay, so that's the major difference between the two. Now, radioactive decay, which is also called as nuclear decay. So what is a nuclear reaction? A nuclear reaction usually involves one isotope of any element will undergo a nuclear reaction and it will produce some sort of particles, and it will always involve a lot of energy. And these particles that it produces, these are referred to as the radioactive decay. So this nuclear reaction is referred to as the nuclear change or radioactive decay. Why decay? Because your isotope is decaying. You're losing that isotope. For example, if you start with U and it changes to Ba and Kr, over time you're losing your U. So the U is decaying because there's no more U left. So that's why it's called decay. Okay. So first thing, why does it undergo radioactive decay? Because your isotope is very unstable. And what makes an isotope unstable? It's the composition of the nucleus. If your nucleus is unstable, which means the number of protons and neutrons that are there, it's not a very good number. It's not a very good balance between the number of protons and neutrons, and it becomes unstable. And when it is unstable, it will undergo radioactive decay and it will produce something which is more stable. Okay, and it will produce in this process a lot of energy and maybe some extra particles, which is called the radioactive decay. If, as long as this product which is formed is stable, great. But if it also is also not completely stable, it can further undergo radioactive decay. So it's a continuous process until you reach a stable nucleus. Okay, so this process is called radioactive decay. It's also called the nuclear decay. Why? Because the nucleus is decaying. All of this is happening from the nucleus. So it's also referred to as nuclear decay. And the atom that undergoes this is called the radioactive atom. It produces particles, nuclear radiation, and some energy. Okay. And this always occurs spontaneously. Spontaneously means it is a natural process. It will occur on its own. Nobody's controlling it. You are not giving it extra energy from outside. It is a spontaneous process. It will occur in nature by itself. These are some types of particles that are produced in a nuclear reaction. We will look into each of these particles in more details in a little bit, but this is a summary table. And as long as you remember this summary table, you're good. Okay, so make sure you memorize this. Alpha particle, beta particle, positron, protons, neutrons, and gamma particles or gamma rays. These are different types of particles that are usually produced in a nuclear reaction or usually involved in a nuclear reaction. What is an alpha particle? Remember their symbols because that's the most important part. In case of a nuclear reaction, what is the most important parts? There are two things that are most important. One is A, which is the mass number, and the second thing is Z, which is the atomic number. Okay, so remember this part. These two are most important in a nuclear reaction. Why? Because these numbers represent the nucleus, and in a nuclear reaction, a nucleus is involved. Okay, so each of these symbols, you will see their own Z's and their own A's. Okay, so remember the symbols. An alpha particle is represented by alpha. It is written as alpha, or it can be written as alpha 2, 4. These numbers you just have to memorize. Okay, it's 2, 4, which is very similar to helium. So if you remember, if you know helium, element from periodic table, helium has 2 protons and 2 neutrons, so therefore total mass number is 4. So that's why it's also sometimes referred to as helium. It's high energy particle, helium nuclei consisting of 2 protons and 2 neutrons. A helium atom would also contain 2 electrons, but this is not helium atom. This is just the nucleus of helium. Okay. Second particle is beta particle, which is high energy electrons. Again, this is not an atom electron. This is just a beta particle. This is not electron. This is very high energy electron. Okay. And just how an electron has a charge of -1 and mass is 0, the same is true for this, but this is usually written for electrons, whereas for beta particle, instead of using E so we don't confuse it with an electron, we usually use the symbol for it as beta. Beta is -1, 0. Positron is basically opposite of a beta particle. Okay, so positron means it's a positively charged electron. Okay, you can also remember this as positively charged electron. It's a particle which has the same mass as an electron, basically 0, but has a charge opposite to an electron, so it is +1. It's also written as +1 electron. Again, it's also written as beta, but a positively charged beta particle. Okay, particles with the same mass as electron but with a +1 charge, or a 1 unit of positive charge. Okay, then the next one is proton. Protons, we already know, is represented as 1, has a +1 charge and a mass of 1, so it's same as proton. Sometimes, because hydrogen also has 1 positive charge has 1 proton in the nucleus, and mass number is also 1, so it's also sometimes represented as a hydrogen. It's a nucleus of the hydrogen. Okay, only the nucleus of hydrogen atom. It's not hydrogen atom, it's just the nucleus of the hydrogen atom. Neutron, again 0 charge, +1, so you already know this. This is basically a particle with the mass approximately that of a proton but a charge of 0. Okay, and then there's gamma rays. Gamma rays is represented by the symbol this, which is like almost like a Y, but with this longer part at the bottom. This is gamma rays. These are very, very high energy radiation, so most of the nuclear reactions are accompanied by these high energy radiation. So it's not really a particle, it's just energy. Okay, so remember this table and their symbols. Now let's look at writing these nuclear reactions. Okay, so what does a nuclear reaction involve? A nuclear reaction would always have a radioactive isotope which will turn into some other isotope which is referred to as the daughter isotope, and it produces some energy and some particles are also produced. Okay, so this is called a nuclear reaction. How do we write a nuclear equation? Just how chemical reactions are written as a chemical equation. For example, carbon plus oxygen gives you CO2. That is a chemical reaction, right? What is important in a chemical reaction? It should be balanced, right? But what are we balancing here? In a chemical reaction, we balance the number of atoms, right? If your reactant has 1 carbon, product has 1 carbon. Reactant has 2 oxygen, product should have 2 oxygen. So that's a balanced chemical reaction. But when we write a nuclear reaction, we don't balance the atoms. What do we balance? We balance their Z and we balance their A, which means on the reactant side, the total A should be equal to the total A on the product side. Same thing is true for the Z. The total Z on the reactant side should be equal to total Z on the product side. For example, this is a nuclear reaction. U changes to THHE. You can see this is one atom, completely different atom. So that's how we know it's a nuclear reaction. If you see what is my atomic number, mass number here, the superscripts, 238. What are the total superscripts here? 234 plus 4, which is 238. So this should be balanced. Also in the subscripts, which is atomic number. On the left, it is 92. On the right, 90 plus 2, which is also 92. So these numbers should be balanced. As long as they are balanced, your reaction is, nuclear equation is, equation is balanced. So in this example, you can see this reactant is decaying by what? During the decay, it is producing an alpha particle. Okay, so this is one of the examples. Question could be just to either balance your nuclear reaction or predict what is your product just based on balancing. For example, this question, TL decays to PB and one other product. What is that other product? So it tells you it's a decay, which means it's a nuclear decay or a radioactive decay. So TL210, because it's given, it's a mass number, gives me PB lead 210 and one more product. Okay, I have to figure out what this is. Okay, so let's assume it's X. Okay, so I need to find these two numbers and then I need to find what is my x. How will we find it? You add all these superscripts and it should all be equal on both the sides. What is it on the reactant side? 210, which means on the product also it should be 210. This is already 210. What should I add to 210 to get 210? A 0, which means the superscript here is 0. Now let's go to subscripts. I don't see any. So what are my subscripts? Remember, these subscripts are the identity of the atom, atomic number. Where do you find it? Periodic table has it. Okay, so even if they're not given to you in question, you can get this information from periodic table. Find the element TL on periodic table and find its atomic number. Atomic number for TL is 81. Atomic number for PB, lead, is 82. What's the total on the reactant side? 81. Product side, 82 plus something should be equal to 81. What should I add to 82 to reduce it to 81? I should add -1. So what is this number right here? -1. Which means, do we know any particle which has a -1 charge and a mass of 0? It is beta particle. -1 with a 0. This is from the summary table. Okay, so that's why you need to remember this. Which means, what is the other product? The other product is a beta particle. Okay, let's try some more of these examples. And in this, now we'll also get to more details about all of these particles. There's not too much detail here that you need to know, so we'll just go over them briefly. But what you should remember is how to balance these reactions. Okay, so for example, this is alpha decay. This element that's given to you, or this atom, is undergoing alpha decay. Can you complete this reaction? Okay, it's producing 1 alpha particle, let's assume. Okay, so can we complete this reaction? Ra22688, decaying by alpha, which means my product is alpha. Remember that. If it decays and produces alpha, it's a product. What is alpha? 24. That's alpha. Which means if the bottom here is 88, this is x. I just need to find what are my two numbers. If I know the two numbers, I can find what is x. Okay, this is 2 plus something should be equal to 88. What is that something? 86. So that's my bottom number. Okay, similarly, what's the top? 226. What's the top? 4 plus something should give me 226, which means what should be what should be added here? 222, which means this number is 222. So I've figured out my superscripts and subscripts. Now the question is, what is x? What is x? How can we find this? To find this, you need to find the atomic number and find the identity from the periodic table. What is the atomic number, element with atomic number 86? The periodic table tells me that is Rn, which means my x is Rn. So what is my complete overall reaction? I'll replace this x with Rn86,222. That would be my complete balanced reaction, as you can see right here. Okay, now for every alpha particle emitted, A decreases by 4 because you're losing 4, and Z decreases by 2 because you're losing 2 right here. Okay, this is the most common form of decay for a heavy unstable nucleus. Okay, what does a heavy unstable nucleus mean? If your Z is greater than 83, most of the times it will undergo alpha decay. Okay, as long as your Z is greater than 83 and your A is greater than 200. You can't find this number on periodic table, so most of the times we ignore this. But remember, Z greater than 83 usually will undergo alpha decay. So it's the most common form. Next is beta decay, which means it involves ejection of beta particles, or it produces beta particles. For example, this is my reaction, nickel 2863. It produces beta, which means beta means -1, 0. That's my beta particle. And nickel 2863. So what would be my other product? I'll assume it's X. Subscript 28. So on this side it should also be 28. Total -1 plus something is 28, which means that something is 29. Superscript 63, which means this total should be 63. So 0 plus something 63, so that something is 63. Now what is X? How do we find it? If you look up periodic table for the atomic number 29, it is copper. So it gives you copper 29. And in this case, you can see the number, mass number stays the same, 63, 63. N increases by number 1 and Z increases by 1 as well. You don't have to memorize this part. I mean, it's understandable from here. You can see it from here. You don't have to know this part. Okay, this is just describing it. But where do you find this decay? It is observed in the nuclides with a large N to P ratio. Most of the times, if N over P, N means neutrons over protons. If this ratio is really high, it undergoes beta decay. Next is positron emission. Again, let's complete this equation. Carbon is producing positron. So what is a positron? It's also a beta particle, but with a positive charge. So what should be the X right here? This is 6. So this should be +1 plus something should give you 6, which means it's 5. This is 11 on this side. 0 plus something should give you 11, which means this is also 11. So what is the element that has atomic number of 5? It is boron. So it's 5, 11. Okay, this is a positron. It is also called as an anti-electron because it's basically oppositely charged as an electron and is the anti-particle of an electron. It is usually observed in the nuclides in which N to P ratio is low. If your neutron to proton ratio is low, that's when we use this. That's when the nucleus will usually decay by positron emission. Then we have electron capture. Okay, so this is a little different. This is called electron capture. This was not listed in that summary table. What is electron capture? Electron capture occurs when an inner shell electron combines with a proton and is converted to a neutron. Okay, so one electron from the shell will react with one of the protons. Okay, and it will produce neutron. How? -1, +1. Total becomes 0. 0 plus 1 becomes 1, and that is for a neutron. Okay, for example, Fe26 undergoes electron capture. Can you complete the reaction? Okay, how would this occur? This will be provided to you, and the question says undergoes electron capture, which means it adds an electron. Okay, so what will it produce? 26 minus 1, which gives you 25 and 55. So you find this 25 from periodic table and it is manganese. So that would be your product. Where would it occur? It would occur for proton-rich nuclei. If your nucleus has a lot of protons, if it's unstable because it has a lot of protons, one electron will come and combine with the proton. It will destroy the proton, becomes a neutron, which means a proton is gone and is replaced by a neutron. Then we have gamma emission. Like I said, gamma emission is basically just very high energy radiation. Photons means radiation, right? Light. Gamma emission usually occurs together with other forms of radioactive decay, which means most of the nuclear reactions will produce lot of G is emitted. Usually it's written as, well, it shouldn't be G. I think most of the times this is the symbol that is written. It's a gamma. Gamma is written like this. G is probably just my PowerPoint is writing it as G, but it should be gamma. Gamma or G just means lot of energy is involved. For example, in this reaction, it is decaying and producing alpha particles, but because it's a nuclear reaction, there's usually along with the particles a lot of energy released, and all that energy is referred to as gamma radiation. Okay, several photons of different energies can be emitted from an excited nucleus as it turns into the ground state, meaning it's just going from unstable form to a more stable form. Okay, so whenever gamma emission occurs, there's no change in your A or in your N. So your mass number or atomic number never changes as long as it's only gamma emission. Example like this, Complete the following radioactive decay equations and identify the radioactive process. Okay, so again, how do you find it? You balance your top and the bottom numbers on the two sides. This is 11 plus something gives you 11, right? Because total on this side is 11, so on both sides it should be 11. So what is this number right here? 0. Okay, the bottom is 6 plus something should give you 5. This is 5. 6 plus x should be equal to 5. So what is this x right here? It should be -1. What is something that has -1 and 0? Beta particle. -1, 0. So that is your unknown here. The next reaction, 222 should be equal to 218 plus something, which means what is this something? This something is 4. Okay, next I have at the bottom 86 equals 84 plus something plus this number. Okay, which means what is that number? That should be a 2. Okay, which means 2, 4 is released. And what is this particle? Alpha particle. Okay, so that's an alpha particle. Next example, 6 on the product side, sorry, reactant side, is equal to 7 plus something. I'm doing the bottom ones, which means what is that something? That something should be -1. Okay, and this is 14. 14 meaning this should be 0, which means what is being released? -1, 0, which is what? A beta particle. Okay, the last one. Oh, nothing is known. Okay, they don't tell you what any of this is, which means I need to find what are the symbols, and I also need to find these superscripts. Okay, so what is this symbol right here? 9, which means how can I find it? From the atomic numbers. 9 is the atomic number for, what do we know from periodic table? If you look it up, it's fluorine, which means 918 gives you 8 something. The atomic number 8 is for oxygen, so I have figured that out as well, which means what should be this? How do I find this? I don't even know. Why? Because the other guy is also not known. So we will let's first solve the bottom ones. Okay, so if we solve the bottom, this is 9, this is 8, which means 9 should be equal to 8 plus something. What would be that something? That something would be +1, right? So this should be 1, which means this is a 1. Okay, which if this is a 1, means it's a +1, and we only know one particle which has a +1, which is a positron, which means this is a +1, and I know what positrons are, mass of 0, which means I figured this out. So I can now solve for the subscripts. This is 18 superscripts. This is 18 on one side, on the other side it should also be 18, equal to 0 plus something, and what is that something? 18, which means my answer is 8018 gives me a positron. So that's how you can solve these nuclear reactions or complete these nuclear reaction equations. Okay, the next part, radioactivity. So how can we measure this radioactive decay? The radioactive decay is measured by a device called Geiger counter. It is a device that can detect radioactive decay, which is also referred to as the disintegration. Why? Because your nucleus is decaying in this process. It is disintegrating. The particles are being released from the nucleus. That is why it is called disintegration. Okay, the rate of decay is called as the activity of a sample. Any radioactive sample has there are some terms that I use. For example, radioactive decay, radioactive disintegration. There's also a term called as activity, which just refers to the rate, speed of the decay, the speed of a reaction at which it is occurring, a nuclear reaction. That's called activity. And this speed is usually given by the number, how many disintegrations are occurring per unit time. So how many disintegrations per unit second, or how many disintegrations per unit minute, or how many disintegrations per hour. So basically that's the speed of the reaction. Okay, other units that are commonly used is becquerel, BQ, or Curie. Curie, you might have heard of this before, Madame Curie, right? So that's exactly what it is based off of. Okay, so 1 BQ is equal to 1 disintegration per second. 1 Curie is equal to 3.7 times 10 raised to power 10 becquerel. You don't have to memorize this. Okay, these are just some conversion factors. If question is asked, it will be given to you. Okay, so a sample activity is usually expressed per gram, which means how many disintegrations are occurring per second per gram, or how many Curie per gram. Why? Because the radioactive decay or a nuclear reaction decay or rate is dependent on number of atoms. More number of atoms means more grams, right? More mass. So it is dependent on mass of the atoms that you have. If you have more atoms, it will undergo more faster decay. If you have less atom, it will undergo slower decay. So that's why this is also included in the activity. The activity is usually, the unit of activity is usually how many disintegrations per unit per gram of an atom.